Hi, so this is the third video in a series of videos that I'm making about how to solve the Atwood's machine via various methods from physics. So just remember that the Atwood's machine is defined as a system of two masses hung over a pulley, where one mass is heavier than the other, so it will fall, and the other mass will rise. And in this case, we're dealing with an Atwood's machine where the pulley also has mass, which means that it has some inertia to it, so the whole system will move slower than if the pulley did not have any mass. For this video, we're going to be using some real numbers. We're going to take the bigger mass, MB, is 10 kilograms, the smaller one, MA, is 5 kilograms, the pulley is 1 kilogram, and then the height H, big H, where the bigger mass, MB, starts, is 70 centimeters away from a table. We'll take little h as 20 centimeters, which is the height that the smaller mass starts, and the radius of the pulley as 20 centimeters. And we're also going to say that the system starts from rest. Now for this, we're going to be using energy concepts, so this is something that you'll see later on in your intro physics courses. The way I've showed you before was maybe some things that you would see earlier on in your physics courses, just dealing with kinematics. We're going to here use energy concepts. So these are some of the questions that you would be asked whenever you're dealing with the energy concepts at Atwood's machine. How fast is the bigger mass moving the instant that it hits the table? And then what fraction of the kinetic energy is in the rotation of the pulley at the instant when the mass hits the table? The first thing we're going to do is set up the conservation of energy. So in the energy chapter, anytime you see a question that's asking you things about energy, you should think conservation of mechanical energy. And conservation of energy simply says that the initial energy that the system has is equal to the final energy that the system will have. The initial energy is the initial kinetic energy plus the initial potential energy. So we use K to mean kinetic energy and U to mean potential energy. And the final energy is the final kinetic energy plus the final potential energy. The first thing that we can do is see that the system is released from rest. This is given in the problem statement, which means that the initial kinetic energy is 0. This should always be on your mind whenever you see an energy problem, that at some point it will say, perhaps, that the system is released from rest or something like that, which is an indication that the initial kinetic energy is 0. So the initial energy is equal to only the initial potential energy. So then we can break this apart and say that the potential energy is the potential energy in each of the three things, the mass A, mass B, and the pulley. Each of these has some potential energy in it, and we'll write down what that is later. For the final state, we know that things are moving. We're defining final to mean the instant that mass B hits the table. So at that time, all three things are moving, so Ka, Kb, and Kp. You will have kinetic energy, and all things will also have a potential energy, except we can decide in these problems where to set the gravitational potential energy to 0. Basically, where to set y equals 0 or h equals 0. And if we do that, we can put the potential energy equals 0 at the table, and that means that mass B at the final state has no potential energy. We've defined it as such. And so we can equate the initial energy, which is only the potential energy of each item, with the final energy, which is the kinetic energy of each, plus the potential energy of mass A and of the pulley, because the potential energy of mass B is 0 at the table. The next thing to note is that the pulley does not change its height. And remember that the gravitational potential energy that an item has is related to how far away it is from where we set 0 to be. The pulley does not move up or down during this whole event, so UPI and UPF are the same. That's on both sides of the equation, so we can subtract it away, and we only have that the initial potential energies of masses A and B is equal to the final kinetic energies of A, B, and the pulley, plus the final potential energy of mass A. So now we need to fill in each of these terms using the formula that we know for kinetic and potential energy. Our next step is to fill in each of the terms in the equations that we had. So remember that what we have here is simply that the initial mechanical energy equals the final mechanical energy. We've reduced this to saying that the initial energy is simply the initial potential energy of each mass, and the final energy is the kinetic energy of each mass and the pulley, plus the final potential energy of mass A. So now recall from class that the gravitational potential energy for some mass m at a height h is mgh, where g is the gravitational constant on Earth, the gravitational acceleration. And the kinetic energy for an object moving is 1/2 mv squared. I say k linear. It doesn't have to be moving exactly in a line, but I just mean not rotating. Whereas the kinetic energy for rotation we can write as 1/2 I omega squared, where I is the moment of inertia for the thing that's rotating, and omega is the angular speed that it's rotating at. So now we can fill in our terms. We have UA initial, the initial gravitational potential energy of A is MAGH, little h is the height that one starts. For mass B, we have MBG big H, because that's the height where the bigger mass starts. And the final potential energy of A is MA times G times its final height, and it starts at a height H, and then you want to know where it ends. Well, these two masses are connected, and if MB moves down by H, then A has to move up by big H. So the final height of MA is little h plus big H. For the kinetic energy of A at the end, this will be 1/2 MA V squared, where V is going to be the final speed that this mass is moving, which is the same for both masses because they're attached. So for B, it's 1/2 mb v squared. And for the pulley, we have 1/2 I omega squared, or I've just written the moment of inertia of the pulley. But recall that for a disk, the moment of inertia is 1/2 mr squared. And omega, here is the rotational speed, we can write as the velocity, the speed of the edge divided by the radius. Remember that the omega is measured in something like radians per second. You could measure it in RPM or something like that, but we measure it in radians per second. So you can need to take your speed and divide by a distance to get rid of the distance in, say, meters per second. So that's how you can remember that. So if you put this in, we have 1/2 times 1/2 mpr squared times omega squared, which is v over r. So now we have an r squared and a 1 over r squared. We can cancel them. We can multiply the 1/2s together and get that the kinetic energy of the pulley at the end is 1/4 times the mass of the pulley times v squared. So if we put all of these terms together, this is what the equation that we get out. So we'll go through. The initial potential energy of mass A is MAGH. The initial potential energy of mass B is MBG big H. This is equal to the final kinetic energy of mass A, which is 1/2 MAV squared, plus the final kinetic energy of mass B, which is 1/2 MBV squared, plus the final kinetic energy of the pulley, which is 1/4 MPV squared, plus the final potential energy of mass A, which is MAGH plus big H. So now we need to solve for the speed. We have this long equation where there's only one unknown, which is the speed v. So we can start doing some algebra to this. First we can distribute the MAG through the parentheses that say little h plus big H. So we'll get two terms out of that. And then we recognize that there is this term MAGH on both sides, where h is little h. So if we subtract that from both sides, we simply cancel that term. Next, we subtract MAG big H from both sides so that the things on the right all have the V in them and that the things on the left have no V in them. And because both of these terms have a G times an H, we factor that out and we have MB minus MAGH equals 1/2 MAV squared plus 1/2 MBV squared plus 1/4 MPV squared. Now everything on the right has a v squared in it, so we can factor that out, and we get this coefficient with the masses and these fractions, all times v squared, and the thing on the left is the same as before. So now we can divide by the coefficient on v squared and get this fraction, mb minus magh over 1/2 ma plus 1/2 mb plus 1/4 mp equals v squared. And I think this is a good place to start plugging in our numbers. V squared is as easy to calculate as v. Of course, you could put a square root over all of this and put the numbers in after that, or we can just put the numbers in now and then take the square root. So we have mb minus ma, that's 10 kilograms minus 5 kilograms, times g times h, so times 9.8 meters per second squared, times 0.7 meters. Remember to convert your centimeters to meters. This divided by 1/2 times 5 kilograms, which is MA, plus 1/2 times 10 kilograms, which is MB, plus 1/4 times 1 kilogram. So if you put this in your calculator, you'll find that the number that comes out is 4.426, and the units work out to meters squared per second squared. It's because this is V squared. So you take the square root of that, and we have that V equals 2.1 meters per second. And this is our answer to the first part of the problem. Okay, so we're moving on to the last part of the problem, which asks us to solve for the fraction of kinetic energy in the pulley. So this is what we have from before. The kinetic energy in the pulley is 1/4 mp v squared, and we know that the total kinetic energy at the end is just the sum of each kinetic energy, so 1/2 ma v squared plus 1/2 mb v squared plus 1/4 mp v squared. And what we want is the ratio kp over k total at the end. This is the fraction of kinetic energy that the pulley has compared to the total kinetic energy. So we can put the numbers in. We have that the kinetic energy of the pulley is 1/4 times 1 kilogram times v squared, which we solved for before is 4.426 meters squared per second squared. And this comes out to 1.1065 kilograms meters per second squared. And of course, a kilogram meter per second squared is a joule. So we can write that the final kinetic energy in the pulley is 1.1065 joules. And the total kinetic energy, the kinetic energy of all three things that are moving at the end, 1/2 ma, which is 5 kilograms, v squared, plus 1/2 mb, v squared, 10 kilograms, plus the kinetic energy of the pulley, which we can just drop in as 1.1065 joules, or you could put the 1/4 mpv squared back in, but you get the same number. And when you add all of these together, you find that this is 34.3 joules. So the fraction here is 1.1065 joules over 34.3 joules, or 0.0322, or 3.2%. This is the last thing that we were asked to solve for. 3.2% of the kinetic energy is in the pulley. The rest is in the motion of the two masses. That's it. Thanks.